Everybody. Just want to make a little video, kind of some college algebra, trig type stuff, just to get you a sense of who I am as an instructor and my approach to things. Um, the the majority of the video, well, all the videos in this course were made by somebody else, so it's not my form of instruction or my way of thinking about things that you're going to be seeing when you do the instruction. I really encourage you to reach out to me if you have questions, because I think that it's important that you know that I'm there for you, and that I have my own way of explaining things, and you may find that useful if you're really struggling with the course. So I'm just going to talk a little bit about the unit circle, because I think it's just been teaching trig recently the last couple of semesters, and I think it's so important to understanding some of the parts of calculus that people often find confusing. Okay, come on, give me some, I just want a right triangle. All right, fine. So the basic, that is not a right triangle, but whatever. The basic concept of the unit circle is that we can use this as a mental tool to help us think about specific, whoa, what's going on there? Specific trig values. And so in particular, thinking about the first quadrant, 30, 45, 60, 90, those are values that you should know. And if you haven't thought about them in a while, maybe it's a little bit rusty, but this is definitely something that should be a part of your memory banks. And I'm just going to kind of build through where these numbers come from. And then we'll talk a little bit about trig functions and solving trig type of problems and where they may show up in calculus. So let's say this is a 30, 60, 90 triangle. So in a basic 30, 60, 90 triangle, let's say this is my 60 side, this is my 30 side. I know that the 30, 60, 90 triangle is 1, 2, square root of 3. Now, if I put them in order of size, that's 1, square root of 3, 2. You can take the square root of 3 with the calculator and see it's like 1.7 something. So now I'm going to place them in the triangle based on which angle they're across from. Now, the smallest side goes with the smallest angle, so this would be 1. The biggest side would go with the biggest angle, so this is 90, this would be 2. And the middle side goes from the middle angle, that would be the square root of 3. So this sets up with a basic understanding of trigonometry, the 3 trigonometric relationships, SOHCAHTOA, and we're going to focus mostly on the sine and cosine. But it gives me a couple things that I can start to build off of. Sine 30 is 1 over 2. Cosine 30 is the square root of 3 over 2. And sine 60 is the square root of 3 over 2. And cosine 60 equals 1/2. Okay, so that's some of the numbers that I need for my coordinates here. The other triangle that I use is the 45, 45, 90 triangle. And of course, if I have a 45, 45, 90 triangle, that means that I really have an isosceles triangle, because these two legs would have to be the same. So I usually just call this 1, 1, and then do the Pythagorean theorem to find out that this is the square root of 2. So then that means that the sine of 45 and the cosine of 45 are the same, which is 1 over the square root of 2. Now, a lot of times math textbooks will rationalize that. So it's the square root of 2 over 2. And that sets up a nice little pattern, actually, because if you think about the order 1/2 square root of 2 over 2, square root of 3 over 2, these are just advancing steps of a quarter, 2 quarters, 3/4, 4/4, but with the square root taken of each one. So it's a sequence essentially where we get bigger in non-linear increments. Okay, so let's start filling it out. In terms of the XY coordinates of the unit circle, the X is associated with cosine and the Y is associated with sine. And one of the ways you can think about that is just by looking at this very first triangle in here. I'm going to use a different color. Let's just use red here. So if I kind of imagine a triangle here, the X value is going to be related to the adjacent side of this angle, and the Y value is going to be related to the opposite side. So that's where those two things come from. And so now I'm going to start filling it out. Just try to get rid of that red. Okay, perfect. This is the X value of 1, the Y value of 0. That's my first point. Next point is for 30 degrees. Cosine is X, so square root of 3/2, 1/2. Next one is the same, square root of 2/2, square root of 2/2. And then we switch it, 1/2, square root of 3/2. And finally, coming up to 0, 1. Everything else from there in the other quadrants are all just reflections of those. So really, you only need to know the first quadrant in order to be able to know all the rest of those. What does it matter? Well, in terms of exactness, you know, there's definitely going to be times when you're finding the cosine or sine of something and you need to have the exact value. And so having these is an important attribute that you want to be able to access. Let's talk a little bit about some trig functions in terms of their graphical representation. So let's see. Let me get rid of all of this stuff, which is really the groundwork for our unit circle. So if we're looking at a function f of x equals sine x, we can use the unit circle to help us think about it. So we're looking at the y values of my unit circle. Those are the sine values. And the inputs here are radians typically. Always think in terms of radians when we're talking about functions. So sine of 0 is 0. And it goes up from there. So 30 degrees equals pi 6. So we're going up. We hit our peak at pi halves. And we come back down to 0 at pi. And then we flip it over to the negative side. And we're at 3 pi halves. And we're at 2 pi here. So this is a full period for sine x. Of course, cosine x, similar shape, but it starts in a different point, which is that the maximum is actually at 0, and we decrease from there, hitting 0 at pi halves. Then we float down to our minimum. That happens at pi. And then we come back up, and we're up here at the top at 2 pi. Okay. So, you know, back in the time you did college algebra, you would have thought about decreasing intervals, right? So that, like for cosine, a decreasing interval goes from 0 to pi. Remember these signs here, this is the exclusive symbol because at the point 0, at the point pi, at the point 0, it's neither increasing nor decreasing. Then we have an increasing interval from pi to 2 pi, right? And what would it be for sine? So if I were just going on the 0 to 2 pi scale, I would include 0. It is increasing at 0. And going up to pi halves, not including that, this is increasing. It's then decreasing from pi halves to 3 pi halves, non-inclusive of either of those 2 points. And then again, increasing from 3 pi halves up to 2 pi. Again, including 2 pi, but excluding 3 pi halves. Now, last thing I want to say is just a shout out to transformations. And I think that trig transformations, or especially sinusoidal functions, is a really great place to think about the difference between the dichotomy that I like to think about is the inside-outside switch. So I don't know if you've talked about that or thought about that in a while, or how your instructor presented it to you back in the day. But basically, I like to think of 2 tables when I think about transformations. I like to think about the stuff that happens inside and the stuff that happens outside. So first of all, the stuff that happens inside is stuff that affects my function horizontally, and outside is stuff that affects it vertically. Inside is counterintuitive, so it generally happens the opposite of what I would think it should be. Outside is intuitive. Inside has to do with X, outside has to do with Y. Some of this is a little bit false in terms of the dichotomy, just in the sense that when I make a change in one thing, it's going to also have an impact on another thing, right? So for instance, a classic example of that is f of x equals the square root of x. If I put a 4 inside, that's exactly the same as putting a 2 outside. So I can really think about this in 2 ways. One is I can think about this now. Multiplying is generally, intuitively, multiplying should be a stretch. So I can think of it outside as an intuitive stretch. So instead of going like this, I'm pulling it upwards. So it goes like this. But if I put it inside, it's counterintuitive. And if I think about how that plays out, it just means that my function that looked like this is being shrunk back towards the x-axis. But of course, shrinking it back towards the x-axis is really the same thing as a vertical stretch. So I think that can be a little confusing. And so one of the things I think is nice about the trig section is when you look at sinusoidal functions and you're saying like, okay, I've got, f of x equals 3 sine 2x plus 4. All of these numbers really do different things. You can see them very distinctly, right? So the 3 is a stretch. So this would be my other table here, which is the basic operations and what they do. So there's basically 3 types of things that you're going to see. Multiplication or division would be a stretch or a shrink. Addition and subtraction would be a shift, or if we want to use a fancy word, it's a translation. And last but not least, if we multiply by -1, that's just a flip. So times 3 outside, that's going to be something that affects this function vertically, and it's intuitive. So I'm going to think of multiplying by 3 as a stretch. So I take my function, which is originally like this, and I say, well, I'm going to stretch this. So the first thing I'm kind of visualizing in my head is now this thing is going higher and lower. But times 3, when you take something like 0 and you multiply by 3, it doesn't change the value of it. So times 3 impacts something more if it's higher up. All right, so then the +4, I'm actually going to do all the vertical stuff first. The +4 is a vertical change as well, but this one is a shift or a translation. So +4 is just going to move this red graph up. So now instead of being centered at 0, 0, I actually move that point up to 0, 4. So I'm looking at something like this. Okay. And finally, this change is the hardest one for most students to kind of wrap their heads around. This would be a horizontal change because it's inside. No parentheses here, but sign kind of marks the boundary between what's inside and what's outside. The things that are outside sign are outside in terms of the transformation. Things that are inside are inside. And so the horizontal change here is going to be a stretch or a shrink. And the way I know which one it is because it's counterintuitive. Times 2 should make something bigger. Multiplying by 2 makes it bigger. But inside, that's counterintuitive. So it's actually a shrink by a factor of 2. So now this, and I'm going back to the version without the horizontal, the vertical shift. It just happens twice as fast, right? So this is a period adjustment for sinusoidal functions, where instead of the period being 2 pi, the period would be pi. So now you get 2 periods inside of that standard 2 pi. And let me make a quick plug here for Desmos because I think it's a really powerful tool for you. Okay, so just go to the graphing calculator, and I'm going to graph a bunch of these things in sequence just so you can see it, right? So there's sine x. There's a little wrench over here. I can change. I like when I'm doing, I don't care what the range is, but I want to do this in pi halves. There we go. So sine x, probably don't, I may need that. So I'm going to change the y-axis to -2. Okay. So then I looked at 3 sine x, and that was where I multiplied it by 3. That's a vertical stretch. And then I've got 3 sine x plus 4. That was where I shifted it up. Okay. Looking at that. And finally adding in, and I would just first take these off and look at sine 2x. So this happens twice as fast. This is the purple guy, right? So inside of 1 period, this is a standard period on the red one. Now we've got 2 for the purple. And putting it all together with the vertical stretch and the vertical shift, I end up with this picture. So transformations are a very useful skill. It's can be kind of difficult for students. It depends on the kind of instruction you got and what tools you used. Desmos is kind of it's an interesting case in point because it's like such a useful tool to really see what's happening and kind of break things apart. But also if you rely on technology too much, it can become a stumbling block in terms of what's happening in your head and what you're capable of doing in your head. So this is something to think about. Okay, so that's just a video covering a lot of stuff. I'm here for you. I'm excited about teaching you calc this semester, and I really want you to let me know if you're struggling with the concept. Typically what happens is you'll do some notes, you watch the videos, and then you'll try some problems. And when you're trying the problem, you get stuck. Now, of course, you got the whole Pearson suite of tools to help you get unstuck. But if you want to hear from a real human about how they think about the problem and maybe some of the underlying things, which may be what you're struggling with, all you got to do is send me a text or click the Ask My Instructor button, and it'll send me a message, and then you can say, hey, I'm struggling with this question. Can you make me a little video? And this is how I would do it. So good to have you on board, and look forward to meeting you. this week.